So, okay, hi, hello everyone. So, welcome to the third lecture of this third week, and yeah, so good afternoon to all. So, let me just recall that in the previous lecture, so what we have discussed the notion of so-called unique factorization domain, and what we have tried to define the unique factorization domain contains two parts. First one is about this existence of factorization, and the second one is about the uniqueness. And what we see that this existence of factorization itself puts a finiteness condition on an integral domain, and this factorization condition has been again interpreted in terms of finiteness condition on the principal ideals. Yeah, so here, so let me just here just let me write. So since we are talking of principal ideals, so this statement should be written as R does not contain an infinite increasing chain of principal ideals. Yeah, in the whole thing we have discussed, but that is somehow overlooked because of this so-called human error that you can say. But anyway, we were talking of only principal ideal throughout the lectures, but this word was somehow missing in this statement. Yeah, and then what we saw that this existence of factorization is equivalent to the finiteness condition on the chain of ideals. And then this uniqueness part somehow is equivalent to the fact that every irreducible element should be a prime element inside UFD. Yeah, I mean to say that UFD will have that property that every irreducible element is prime, and that is somehow equivalent to the uniqueness part if you try to see the proposition this. Yeah. And then what we saw that there is a nicer integral domain than unique factorization domain, which do not have, which actually have the finiteness condition in terms of principal ideals. Yeah, that is we have defined as the principal ideal domain. And what we saw that every principal ideal domain is a unique factorization domain, but not conversely. Yeah. And well, so we have seen this much, and so today, so let me again recall from my first lecture that what we have defined the notion of GCD, and this was possible just because if you see the way we have defined this D, it was completely in terms of the by the fact that any ideal of Z is a principal ideal. Yeah, and the D that we get out of generating ideals from A and B is a principal ideal, and that number satisfies the properties of GCD, and that we call as a GCD. But the question is for general, say for example, unique factorization domain, how to define the GCD. Yeah. Well, so here, so today we are going to foresee that, well, in a unique factorization domain, the concept of GCD still holds. And so let us try to see the statement, and the proofs are very similar, and it is in fact intuitively clear. And so I will leave the proofs for you to verify. But of course, you can see by the very statement of the proposition or theorem that they are somewhat clear by the very statement of the theorem that the proof can be done. Yeah. So let us start with the statement, and and I will write it as a proposition. Yeah. So we are moving towards. So here what we have here, R is for us a UFD, so unique factorization domain. And inside this unique factorization domain, if we take two elements A and suppose it is written in terms of their prime factors, so say P1 and so on, say PR is the prime factorization or irreducible factorization. Since in a UFD both are same, so I can call either prime factorization or irreducible factorization, both are same. And if you look B2 with another elements and it has prime factorization, say Q1, Q2, Qs. Yeah. So let's say this prime factorizations. So B, so let me just write down B prime factorization. Yeah. Yeah, then then this divisibility condition A divides B can be interpreted, and it is very easy now to guess what will be the conditions. A divides B implies, so that means A lies inside the factors of B. Yeah, that means the number of factors in A should be less than or equal to the number of factors that are inside B. Yeah, so this implies that this S will be greater than or equal to R. And if you try to see, since these are the prime factors, primes and irreducible are same, and so if you try to write a suitable ordering of this QIs and PIs, then you can see that since both are prime, so one will be the associate of the other. Yeah, and with suitable ordering, with a suitable ordering of these factors, what one can say that factors, say factors Qi of B. So let me write it, Qi of B. What we can see that this prime factors Pi is an associate of Qi, is an associate of this prime factors Qi, and this is of course for at least prime factors Pi are up to R, so for I from 1 to and so on R itself. Yeah, and conversely also, if you have this condition that if number of prime factors in B is more than the number of prime factors in A, and if so happens that all these prime factors of A are associates of some prime factors of B, then one can say, one can check in fact that A divides B. Yeah, so this is the proposition, and using this proposition, so I will not give the proof of this, and that you can try by yourself and you can prove yourself. So using this proposition, one can in fact write down a corollary, and it is for you an exercise to verify that how this corollary follows from this proposition. And what does this corollary says that if you have R here a UFD, yeah, unique factorization domain, and so if you try to take two elements AB inside this unique factorization domain, and suppose both are not equal to 0, yeah, then what you can prove that there exists an element, so there exists D belongs to this unique factorization domain R with the following properties. So the first property is that D divides A as well as D divides B. So D divides A and D divides B. And the second one is that if an element, so if an element, say E inside this unique factorization domain R, such that E divides A and E divides B, this implies that E divides D. Yeah, so and the existence of this element D is intuitively you can see, just one need to write the prime factorization of this A and B and look at the maximum common factors which lies between A and B, and as you can see that element will satisfy these two properties, and such element exists, and this element so just let me write down, note that D is known as the GCD. Yeah, but however since I have written it as a corollary, it is always good to prove it using the proposition, how this corollary follows from the proposition. In that way it will clear what is underlying power that this proposition has. But anyway, intuitively one can actually find this the existence of this D. Yeah, and so just the note that I would like to write it down, that D is called the GCD. So in the above corollary, so D is known as the GCD of two elements known as GCD of A and B. Yeah, and this as you can see that this GCD is defined up to associates. Yeah, so here we are not normalizing this as the in the case of this integers, one can say about the positive GCD or something like that. But here we have no general way to normalize this GCD. And one thing more, that if you try to realize from our previous lecture, for example, in the very first lecture, we have very nice property that the GCD can be written as a linear combination of that thing. For example, here we have written, and that's the thing was possible just because if you try to see that the way we have defined this, and the property that this is a principle is a crucial step here. But in general, since we are in the case of unique factorization domain, and that flexibility we don't have here. And in fact, the question that whether in this case also one can write GCD as a linear combination. And so let me just tell you that in general, this is not true, that GCD may not be always written as a linear combinations. Yeah. And for example, so let me just write down example that actually clear this thing. So for example, and I think you also know this famous example is your, so if you try to look at the polynomial ring with integer coefficients, yeah, and if you think of this as your thing, well, so this is again a promise to prove that this is a UFD, yeah, and in the next few lectures we will be proving, yeah. So let me just again write that to be proved later. And in this, you can see that if you try to take any prime, say P, yeah, if you try to take any prime P, and if you take the indeterminate X, so P and X have GCD, for example, they don't have any common factors, yeah, and you can say that they have, for example, GCD 1, yeah, but as you can see that, this one cannot be written as a combination of P and X with coefficients from Z of X, yeah. So, but one is not a linear combination, so not a linear combination of prime P and X, prime P and X, and here linear combinations will come with coefficients from Z of X, yeah. So therefore this in general may not be true, but well, the concept of GCD do exist in a unique factorization domain, yeah. So by the way, any questions or comments so far? Okay, fine. So let me proceed further. And so now let me again come to the certain properties of this principal ideal domain. And what we know, that is of course a unique factorization domain that we have proven in the previous lecture. And so the very important thing one also happens in this what one should say principal ideal domain is that it has a very nice structure about this maximal ideals, yeah. And I think maximal ideals is of importance in general, because as you can see that the principal ideal domain has a finiteness condition in terms of ideals. And of course the last are the terminating stage, of course will be your full ring R itself in the case of principal ideal domain. But before that you have these maximal ideals. And so these maximal ideals have certain nice structure in the case of principal ideal domain. And so that is the proposition, and I hope you know this very well, that how. So let me just write down R is a PID, and the maximal ideals of R Well, it will be generated by a single element, but what this proposition actually says that the single element that will generate this maximal ideal are actually irreducible elements. The maximal ideals of R are principal ideals, principal ideals generated by irreducible elements. Yeah. So should do you know this result and proof? Should I skip or I should give the proof? Can you say something? Or you can tell me the steps how the proof can be done for this thing. So for example, what we are going to say that if you take any maximal ideal of a principal ideal domain, that will be generated by an irreducible element. Yeah, so actually the maximal ideals are precisely generated by the irreducible elements in a principal ideal domain. Yeah, so let us try to prove it. And so what we are going to what we need to first so let P belongs to RB and irreducible elements. Yeah, so then our aim is first to convince that the ideal generated by this P is actually a maximal ideal. Then how to proceed? Can any one of you say that how can we start the proof? So this is an irreducible element. So what does this mean? That so since it is an irreducible, so only divisors of P are what are the divisors? One can say are units, yeah, well, and P itself. Yeah. And so these are the divisors. And so what does this imply? If you look the ideal generated by units and P, so that will corresponds to what? So therefore what this implies that the only principal ideals which principal ideals which actually contains the ideal generated by P are ideal generated by units and P itself. Yeah, are and ideal generated by units are 1 and P. Yeah, and so therefore, and what we know, other thing we have given that the R is a principal ideal domain. So since R is a PID, so what we know that any ideal in fact is generated, any ideal is a principal ideal. Yeah, since R is a PID implies every ideal is a principal ideal, right? Is principal. And so therefore what we see that the only ideal which contains this ideal are actually 1 and P itself. Yeah, so this implies that the only ideal. So this implications ensures that the only principal ideals which contain P are this and this, and but this implication ensures actually that the only ideals which contains this principal ideal are actually this and this. Yeah, so the only ideals which contains P, ideal P, are the ideal generated by 1 and ideal generated by P. Yeah, and so this is, if you try to recall the definition of maximal ideal, so this is actually the definition of maximal ideal, and hence this implies that P is a maximal ideal. Yeah, P is a maximal ideal. Yeah, now so this is the one part actually what in order to first of all prove this theorem, one need to ensure that, well, we are trying to say that the generators will be irreducible elements. So whether the ideal generated by irreducible elements are maximal or, and this part actually shows that, well, they are actually maximal ideals. And now the question here is that if you take any maximal ideal, now so let M be a maximal ideal, M be a maximal ideal of your principal ideal domain R, then of course this M, since we are in the case of PID, it will be generated by a single element, say B here. Yeah, and since you can write that here R is a PID. Yeah, PID. Now how we can proceed further, and our aim is to show what we need to show, that this B, the element B, is irreducible. Yeah, and how to proceed, I think it is very straightforward. Suppose not, then you will get the proper factorization, and then you can see that this maximal ideal actually is properly contained in some proper ideal, which is a contradiction. Yeah, so suppose not. Yeah, then what we know that B can be written as say A times Q, and where A and Q are not units, A and Q non-units. Yeah, and so therefore what does it mean? That this implies that this ideal generated by B is properly contained in the ideal generated by A, and of course ideal generated by A is properly contained in the full ring R itself. Yeah, and of course so since the maximal ideal B is properly contained in some proper ideal, which is a contradiction, so this implies that B is not a maximal ideal, not maximal, which is a contradiction to the fact that, so contradicts to the fact that this M is a maximal ideal, contradicts that M is maximal. Yeah, and so therefore what we have proven that the irreducible elements actually are responsible to classify all maximal ideals inside a principal ideal domain. Yeah, okay, so far so good. So by the way, any questions or comment, and then we can proceed further.
I have one comment.
Yes.
Is it, I'm asking students, is SAR put both the directions or only one direction? Any one of you?
Both directions.
Both the direction. Both the direction.
Okay.
Okay, so should I continue?
Yeah, just yeah.
Yeah, so now this is about this principal ideal domain and unique factorization domain, and now let me move further. And so there is another nicer concept which actually generalizes this division algorithm for general integral domains. And so let me just recall what is this division algorithm for this set of integers. Yeah, so inside this ring of integers, so what we have the concept of division algorithm. And what does actually it says that, so if you take two elements A, B belongs to Z, and if you take a non-zero, so that you can talk of this divisibility, then what does the property that we have inside integers, that there exist Q and R such that you can write the element B in terms of AQ plus R, where this R is either 0 or this, and this is usually known as remainder, and Q is known as the quotient. And so the R has the property that either R will be 0 or this R will be, if it is not equal to 0, it will be positive, and it can go up to the modulus of it. It can be strictly less than the absolute value of it. Yeah, and so here the very important thing that this ring of integers has the concept that of absolute value, and using this one has this notion of division algorithm. And if you try to most of the time if you try to see the proof that Z is a principal ideal domain, or it is in fact known as Euclidean domain, but even in order to prove this principal ideal domain, at some point you do use this kind of arguments to prove that thing. Yeah, you always look the smallest in order to prove any idealist principle. You look smallest in smallest integer inside that ideal, and then your claim is that it is the generator for that ideal. Yeah. And so one would like to, and similarly in the case of this polynomial ring, also the role of this absolute value. So if you, so this is the first and second one. If you take a polynomial ring f of x, and here you have a similar concept is known as the role of this absolute value. Here is the degree of polynomial f of x. So absolute value here, if you take f, one can define to be this degree of f of x. And using this, one can again talk of the similar kind of thing, that if you take two polynomials, and if you take the that corresponding polynomial is non-zero, then you can write similar expression here also, polynomial ring. And so this is the thing that one would like to extend for general integral domains. And so well, and therefore if you see the very thing that actually somehow these absolute value are able to actually measure the size of the elements. Yeah, so they are able to control the size of corresponding elements to guarantee or to make this element R in between these numbers 0 and that thing. Yeah. And so with these things, one would like to extend this notion of this absolute value or size function, and that with this property, and that in general is known as the Euclidean domain. Yeah. So let me just define this notion, and then we will proceed further. Yeah. So the definition here is that, so of course we have our integral domain, and here what we are going to say that, so we say that this integral domain R is an Euclidean domain. So in short, we will write it as ED if there exists a size function, if there exists a so-called, these functions are so-called the size function, sigma from set of non-zero elements to set of non-negative integers 0, 1, 2, and so on, such that this division algorithm holds, Yeah. So what does it mean by division algorithm? So let me just write down, that is, if you take, so let A and B are two elements from the integral domain R, and of course A not equal to 0. So then there exists Q and R such that this condition that should be satisfies that this element B can be written as this AQ plus R, and either so either R is equal to 0, or this what I would like to say, if it is not equal to 0, then well, sigma of R will be strictly less than sigma of A. Yeah. And here, of course, this size function is always non-negative, and well, you can put this inequality, that is not a problem. 0 is strictly less than sigma of R is less than A. Yeah. But let us try to no need to write this thing. And so let me just give another what I would like to say, another example apart from this ring of integers and the polynomial ring. Then we will proceed further. So by the way, so far any questions or comment? So if not, so let me continue with an example, and I think you are very much familiar with this what one should say, that ring of Gaussian integers. And so let me start with that, and what we are going to show, that actually if you try to look at this ring of Gaussian integers, so Z of I is an Euclidean domain. Yeah. And so I think, can any one of you tell me that what will be the corresponding size function on this Z of I? Yeah, we should take values inside 0, 1, 2, and so on, and we satisfy this division algorithm. Yeah. So if you take any element alpha, where it should go? Yeah. And this is a usual absolute value defined on the set of complex numbers. If you restrict that on this integral domain, so then one can prove that this is the size function which actually satisfies this division algorithm. Yeah. And so in order to show that, what, for example, if you take two elements, so for example, if you take B belongs to say Zi, yeah, and suppose if I take A is equal to 2 times I, yeah, and so for example, how to show that the division algorithm holds inside this thing. So what we are going to see that what we will geometrically, let us try to see that what will be this 2i plays a role. If you look at the ideal generated by this 2i, yeah, so what will be the elements? So well, Zi you can think of as integer or lattice points on this complex plane, and this ideal generated by 2i, if you try to locate the points which lie in the ideal generated by A, so that I will denote by this cross, and the usual lattice points I will denote by dot. And so you can see that this corresponds to, so this is in integer 0.1, this is 2, that will be the element of ideal, and similarly here is there, then here will be the ideal point, and here will be that thing, and then what you have, so here, and then you have here, and then you have here idea point of an ideal, and similarly here you have this thing, and then these are the usual integer points, lattice points, and this will be the point of your ideal, and similarly here, and then you have the ideal point here, and well here, and here, and here, and then you have ideal point here, and similarly you can see that similar thing here also, you can see that is that, and similarly you can see that this the points which lie in the ideal are denoted by this cross, are actually look like this in the complex plane inside this ring of integers. Yeah. And now if you take any point B in this Gaussian integers, then you can find, what one should say, you can find at least one point of the ideal. Say for example, if you take this, for example, if you take point, say here, this one, or this one, or say uh, this one, you can see that you can always find a point inside say inside your ideal, whose distance if you take the distance of this point with that point in the ideal, is always if you try to write that distance in terms of this size function, then they are actually half of the size of this element A. Yeah. So let me just write down what I would like to say, that so 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 B belongs to Zi, so there exists at least one element in the ideal A, such that if you try to write that element as say such ideal A, and let's say that element is say 2q or 2I times q. Yeah, then what you can see that absolute value of b minus 2iq whole square, if you try to see, is always less than or equal to half of the absolute value of the element A. Yeah, that you geometrically you can see that is always possible. And if you try to see, and now if you try to write this thing as R, yeah, then you can see that this is the required element R here that we are looking in the definition of Euclidean domain, and the Q will corresponds to the multiple of this element 2I, which will lie inside the ideal A. Yeah, so these multiples in this case can be interpreted actually are the elements of this ideal. Yeah, and that one can see, because then if you write this whole thing as R, then absolute value of R square is exactly sigma of R. And if you try to see, this is exactly equal to this is less than or equal to, by this thing is 1 by 2 of this thing 2I square. Yeah, and if you try to see, this is strictly less than sigma of R. This is strictly less than absolute value of 2I square, which is, sorry, sigma of A. Yeah, and so this is, if you try to see, exactly 2 is less than 4. Yeah, so therefore what we see that if you take any element in your Gaussian integers, and for example if you take a point 2I, then there do exist at least one point inside the ideal generated by this 2I, whose, if you try to look, the distance is always strictly less than the sigma of A. Yeah, and therefore so you can generalize this argument for any element A, non-zero element inside this Gaussian integers, and so therefore one can geometrically prove that Zi is an Euclidean domain with respect to the size function. Yeah, and moreover one can also prove this thing algebraically. Also one can prove this thing algebraically. And so what I would like to point out here by this example, that so let me just say that usually in the case of this ring of integers, what happens that if one writes this division algorithm with these conditions, then what one can check most of the time that this R and Q are unique. Yeah, but in general we don't need that uniqueness part, and in fact it may not be true. For example, here you may get different different points of the ideal which have which corresponds here, and so therefore uniqueness may not be true in general. Yeah, and that actually we don't need in the definition also. Yeah, so the point I would like to remark here, that one should not be confused about the uniqueness part when generalizing from ring of integers to general integral domain. Yeah, so let me just give a quick algebraic proof of this. And again, so here what one need to start with two elements. AB belongs to Zi. If you take, and of course A not equal to 0, then what we can do, that we can of course if you think of A and B as a complex number, then we can always talk about B by A, which lies inside your set of complex numbers, and therefore so we can always write B as A times W, where W lies inside C. Yeah, but our aim is to somehow show that this division algorithm holds with respect to the size function, and therefore instead of this W we need to find certain elements inside ring of this ring of Gaussian integers which satisfy this division algorithm with respect to the size function absolute value square. Yeah, So therefore W, since it is a complex number, we can always write in the form x plus iy. Yeah. Now what we are going to do, the kind of thing here we have geometrically saw that we need to find the nearest point, nearest integer lattice point to W. Yeah. And so in order to so what we would like to write, that choose nearest Gaussian point or integer point such that Gaussian integer point, let me just write down, that will be of the form this m plus ni. Yeah, so this will be m plus ni, and to choose nearest Gaussian point m plus ni to this point x plus iota y. Yeah. And so how we can do that? So x we need to parameterize in terms of this what I would like to write, m plus x naught, and y we can parameterize as n plus y naught. And here x naught and y naught, that we know that always we can take in between minus half and half. Yeah. And that we can always find the nearest points, integer m and n, which have this property. Yeah. And then now just one need to look at the corresponding element inside the ideal. So now if we take this point m plus ni times a, again you see that this is an element inside the ideal generated by a. And so what we are going to see now here, we need to only see that b minus this m plus ni times a, and that we can take it as a remainder r. Yeah. And if you try to square it, so what we will get, if you try to write down here what we have, this the role of this thing m and n from here. So here b is a times w. Yeah. Yeah. And then if you try to subtract m plus ni times a, then we can see that if you try to write simplified, this will be exactly equal to absolute value of a times x naught plus I times y naught whole square. This is just because this w is x plus iy and x is written in terms of m plus n. Yeah. And now what will be this thing? So this it will be equal to absolute value of x naught plus I times y naught square times modulus of a square. Yeah. And now what we need to estimate this x naught plus I times y naught. And if you see that x naught and y naught both lie between this thing, so this will imply that this whole square will be less than or equal to, so this is absolute value if you try to write, so this will be x naught square plus y naught square times absolute value of a square. And so this will be less than so this will be 1 by 4, this will be 1 by 4, so half of absolute value of a square, which is strictly less than absolute value of a square, which is sigma of a. So what we see that sigma of r is strictly less than sigma of a in this case, and that's the proof about this the ring of Gaussian integers is a Euclidean domain. Yeah. Okay, so far so good. By the way, any questions or comments so far, or uh, any doubts? So if not, so I think let me continue further. And now, so let me prove prove or quote a proposition, I think, whose proof you can try by yourself, that Euclidean domain implies, if you have an Euclidean domain, implies a principal ideal domain. That you can prove by yours. I think I will leave the proof, and the idea is very similar to the way you prove that the set a ring of integers is a principal ideal domain. The similar proof will actually say that Euclidean domain implies a principal ideal domain. Yeah, that means what you have given, you just let me sketch the proof. So what you take any ideal of R, and you need to prove that is a principal ideal. Then what you do, that you look the smallest element inside this ideal, smallest non-zero element inside this ideal with respect to the size function. Yeah, and then the claim should be that this ideal is generated by that smallest non-zero element. Yeah, and in order to prove that actually this ideal is generated by this, one need to show that I is actually contained in the ideal generated by that smallest non-zero element. And in order to prove that, one need to use this division algorithm that we have given in hand. Yeah, here we need to use this division algorithm that we have given inside this Euclidean domain. And using that, we can show that in fact ideal I will be contained in that smallest element inside the smallest non-zero element inside the ideal, and that will actually prove that every Euclidean domain is a principal ideal domain. Is it okay, or I should write the detailed proof? Can you please comment? Please,
It's
you can. Yeah,
it's okay, sir.
it's okay. Anyone else?
Yes.
Is it clear?
Yes, sir.
Yeah, good. So, okay, so far so good. So let me just mention certain things that is here about this ring of Gaussian integers. So what we saw that, so let me again come to this example, and that, so this ring of Gaussian integers, if you try to look, and of course this ring of integers is contained inside this ring of Gaussian integers, and we know that the element 2 is a prime element inside these integers. Yeah, but 2 even is not irreducible element inside this Z of I, because 2 can be written as, if you try to see that, 1 plus I and 1 minus I. Yeah, and similarly 5 is though an irreducible or prime element in Z, but 5 is not even an irreducible element inside this Zi, because again similar way you can see that 2 plus I and 2 minus I are the factorizations in this Zi. However, one can prove that 3 is irreducible element, so 3 also lies in Z as well as Zi, but 3 is irreducible in Zi, that you can prove by yourself as an tutorial thing, and hence prime. Yeah, because we have seen that this Zi is a Euclidean domain, so is a principal ideal domain, and we know that in a principal ideal domain, or even in a unique factorization domain, irreducible is same as prime. So what I would like to just say that here, if you try to look at the prime in numbers which are inside this set of integers, some of the prime numbers stays as a prime inside Zi, and some of the prime numbers even they have proper factors inside Zi. Yeah, and so therefore again then it is a question of investigation or question of discussion, that means that what are the primes are classified the prime integers which stays as a prime inside the set of integers, or what are those things are which doesn't stay as a prime inside this ring of Gaussian integers. Anyway, this goes into the area of number theory, and at some point maybe if, in the coming lectures we will be discussing and looking what are primes which have these properties, and what are the primes which doesn't stay as a prime inside this ring of Gaussian integers. Yeah, and okay, so far so good. So this is about the Euclidean domains, and by the way, any questions or comments? If not, so if you have, you can ask me, and then we will proceed further, and then our aim is to somehow move towards to prove that this polynomial ring with integer coefficients is a unique factorization domain?
No, sir.
Okay, fine. So now let me move towards, and so let me start with a suppose if you have polynomial with rational coefficients, yeah, polynomial with rational coefficients, and as we have seen that this polynomial can be expressed, so since we have seen that fundamental theorem of arithmetic holds in QX in general for any field f and with its polynomial ring, and so therefore we can always write f of x into the factorization c times say p1, p2, and so on pk, right, where this c will be your rational number, and pi's are monic irreducible polynomials in qi, yeah, sorry, qx, yeah. And now the question is that suppose if you have a polynomial with integer coefficient, that means suppose f of x belongs to z of x, yeah, and if you think of this polynomial ring z of x is contained inside this polynomial ring q of x, then well you can factor this f of x inside q of x, yeah. But our aim is to a natural question that I would like to ask, or we would like to understand that can this fx can be factors into zx itself, yeah. So the question that I would like to mention is that can this polynomial fx be factored in zx itself, in z of x itself. So this is the question, and and that is the question that we would like to answer actually. And in fact, what we our aim. So in fact, that is in fact true, and in fact, our aim is actually to prove that this zx is a UFD. Yeah. And so, for example, if you try to see, so before discussing further, so let us start with an example, and then we will continue. So, for example, if you start with this polynomial, say 6x cube plus 9x square and plus say 9x plus 3, and if you try to factor it, so what will be this factorization with integer coefficients, and the factors will lie in zx. If you try to see, so you can see that this will be 3 times 2x plus 1, and then other factor will be x square plus x plus 1, yeah. And one thing that you can see that all are inside this z of x, yeah, as you can see. Now one thing is very if one wants to study the factorization for zx, we need to observe certain things that may not hold with if you try to compare with q of x, yeah. And the one thing that you can see that if you so zx contains z, and the prime integers in zx, you can see that they are actually the irreducible elements inside zx, yeah. So if you look at prime integers, they are irreducible elements. For example, 3 belongs to zx as an irreducible element, yeah. And so therefore so therefore they do occur in the prime factorization, they do occur in the factorization of the polynomial f of x, because they corresponds to the irreducible elements. And the second thing is that what we see from here, that you can see that the polynomials, the irreducible factors may not be monic, yeah, because we are in the case of integers coefficients, and we don't have control on this monicness, yeah. And if we try to fix a monicness, then most of the time we will not be able to factor a given polynomial inside ZX. Yeah, so one will not be able to factor the given polynomial with integer coefficients inside ZX itself. Yeah, and so therefore we have to compromise with these things, that we allow non-monic polynomials in the factorization as well. And yeah, so one thing is that, and the other thing is that, suppose if you have a polynomial f of x, yeah, suppose it is written as a0 plus a1x plus and so on so forth an x to the power n, where ai's are integers. So what can happen, that these coefficients do have a common factor, and it may happen that that common factor might be a prime number which is an irreducible element, and that common factor will come out and it stays as an irreducible factor inside z of x. Yeah, and yeah, so this is the thing. And in order to deal with such kind of thing that do occur, polynomial inside z of x, one is tempted to define certain definition about this primitive element or primitive polynomials. Yeah, and so let me just define those things and then we will proceed further. Yeah, so let me give a definition of that and then we will continue our lecture. So here definition, and what we say that a polynomial, so let me write down a polynomial, say fx belongs to z of x. And this polynomial, suppose if it is written in this way, yeah, is a primitive, is a primitive polynomial, primitive polynomial if what we can put the condition that their GCD of the coefficients do not have any common factor except the units. If its coefficients, say a0 and say an have no common factor, have no common factors except plus minus 1, except plus minus 1, and the leading coefficient. And so since we are not able to restrict the polynomials to be monic, but instead of monicness we are able to focus, we are able to put certain condition on the leading coefficient, and that condition is that the leading coefficient an is positive. Yeah, and so with this definition, so I will stop today's lecture and we will continue in the next lecture, and then we will prove certain properties about primitive polynomials and Gauss lemma, and then we will be proving that ZX is a unique factorization domain, and that in fact the arguments in fact in general will say that this can be generalized for any unique factorization domain R. Yeah, so that is the thing, and so I would like to stop. So thank you very much.